All right, welcome to the deep dive, everyone. Today we're diving into, a pretty profound question. Can mathematics explain anything beyond itself? Like outside its own little world of numbers and equations, we've been really digging into this, spending some quality time with the Stanford Encyclopedia of Philosophy, trying to wrap our heads around it.
Yeah, and for our listeners out there who, well, love a good philosophical puzzle,
Yeah.
this is a real doozy. It's like world of actual explanations.
Right, exactly. So, what we want to do today is, I guess, sort of map out the different ideas about how and if mathematics can really explain things, not just, describe things with equations, but actually make us understand why things are the way they are. We'll be exploring two main areas. First, how does math work in explanations about, the empirical sciences, the stuff we can observe in the world? And second, can there even be explanation within mathematics itself?
Yeah, that second one's a bit of a head scratcher for sure.
Right.
Okay, so let's start with the first one. Math in the empirical sciences. Seems like a natural place to begin, right? I mean, science uses math all the time to describe and model the world. And science is all about explaining why things happen, right? So the question is, can math itself be part of those explanations?
Yeah, totally. The traditional view of scientific explanation is often about finding causes, like what makes a certain event happen. And math is obviously super helpful for like keeping track of those causal relationships. Predicting a solar eclipse, for example, we can use math to map out the movements of the sun and the moon and see how they lead to the eclipse.
Right, like a clockwork universe kind of thing.
Exactly. But things get really interesting philosophically speaking when we start looking at explanations that aren't about cause and effect in that straightforward way. Like, what role does math play in those cases? That's where the debate really gets going. Philosophers have found a bunch of examples where math seems to be doing some explaining, but it's not directly about, this causing that. Like, think about explanations for why something's impossible. Say you've got 7 cookies and 3 friends. You can't divide those cookies equally without breaking one, right?
Right.
And the explanation for that is a mathematical fact. 7 isn't divisible by 3. It's not that something in the physical world is preventing you from dividing the cookies. It's like a constraint built into the numbers themselves.
Yeah, like a rule of the game.
Exactly. And another good example is that classic bridges of Königsberg problem. Why can't you walk over all 7 bridges in the city exactly once?
Yeah, remember that one. Turns out it's because of the structure of the bridge network, how they're all connected. That structure is something we describe using graph theory, which is, well, math. And it's that mathematical property that explains why it's impossible, not some physical obstacle.
So, in those cases, it's like math is showing us the limits of what's possible, not because of physical causes, but because of how things are structured mathematically.
Totally. Then there are explanations for features of the world that seem kind of surprising or especially patterned. Like periodical cicadas, they have these really long life cycles, right?
Yeah.
And often those cycles are prime numbers, like 13 or 17 years.
Yeah, prime numbers, those always seem to pop up in weird places.
Right. So one argument, and this was Baker's idea, is that these prime numbered cycles give the cicadas an evolutionary advantage. Like predators with shorter life cycles that aren't in sync have a harder time catching them. Now, the prime numbers themselves aren't causing the cicadas to emerge every 17 years or whatever,
Right.
but they explain why those cycles would be evolutionarily stable and likely to pop up. It's like a mathematically optimal solution that nature, through evolution, sort of stumbled upon.
That's pretty wild. Nature doing math.
Right. And we see this kind of thing all over the place. Like honeycombs, they're always hexagonal, right? That minimizes the amount of wax they need to store honey. And the way sunflower seeds are arranged in those spirals, that maximizes packing efficiency.
Hmm.
So both of those are like mathematically optimal arrangements.
Okay, I see where you're going with this.
Right. And then you've got Plateau's laws, which describe the angles at which soap films meet. That, again, reflects a principle of minimal surface area, a mathematical concept. Even the Kirkwood gaps in the asteroid belt, those could be explained by the instability of certain orbits due to gravitational resonances, which is a phenomenon we understand through math. And sadly, like bridge collapses, those can sometimes be explained by the math of stability and resonance too.
So it's like this recurring theme, mathematical tools helping us understand the reasons behind these patterns and behaviors. Often it's connected to ideas of optimality, like the best way to arrange things, or stability, like what makes a structure hold up. It's like the universe is speaking in math and we're slowly figuring out how to translate.
Totally. And this back and forth between math and explanation, it's not new. Even Aristotle was thinking about this. He had this idea of mixed sciences, where math provided the reason why for things happening in the physical world. But then later on, especially during the Renaissance, there were these debates, like in the Quaestio de Certitudine Mathematicarum. They were wrestling with whether math, which doesn't directly cause things, could really provide explanations.
So even way back then, they were trying to figure out if math could be more than just a description tool.
Right. And then, fast forward to the 17th and 18th centuries, you have Newton shaking things up. He comes up with these mathematical laws of motion and universal gravitation, and they became accepted as explanations for all sorts of stuff, even though no one really understood how gravity worked at the time. There was this guy, Castell, who insisted that you needed a tangible physical mechanism to really explain something.
So like just having a mathematical equation wasn't enough for him.
Exactly. So you can see how the criteria for what counts as a good explanation were changing. And that evolution continues today. Like, Morrison argues that just because something's mathematically unified doesn't automatically mean it's also physically explained. Newtonian gravity, for instance, it gives you this elegant mathematical framework, but it doesn't initially tell you how gravity actually does its thing.
Right, so mathematical elegance and predictive power don't always equal deep explanatory power, at least not in the physical sense.
Exactly. And as philosophers, of course, we try to fit all these observations into our theories of explanation. Like, we've got Hempel's deductive nomological model, which is all about scientific laws, Salmon's causal mechanical account, which focuses on causal processes, and then all those mechanistic views that are really into figuring out the underlying mechanisms.
Right, the big hitters in philosophy of science. So how do those frameworks deal with mathematical explanations that aren't about direct cause and effect?
Well, that's where things get tricky. Some people, like Barron, have tried to squeeze mathematical explanation into those law-based or unificationist approaches. Others, like Satsi and Pexton or Reutlinger, they've tried to stretch the causal accounts to make room for math. And then you've got folks like Pincock who are like, maybe there are just fundamentally different kinds of explanation, including mathematical ones that don't rely on traditional cause and effect.
So maybe we need to expand our categories to fit these mathematical insights.
Totally. And Lange, he's got this interesting idea. He says that math can explain things because of its inherent necessity. Like, it has to be true. He calls these explanations by constraint. So going back to those earlier examples, like dividing the cookies or the bridges of Königsberg, the mathematical structure itself rules out certain possibilities. He sees a parallel there with scientific laws, which also have this kind of, must be true quality.
So the explanation lies in what's mathematically necessary. That's pretty neat.
Yeah, but of course, there are people who push back on this. Philosophers like Craver and Povich, they worry that if you don't have causality in the mix, the explanation isn't really grounded in the physical world. Especially Craver, as a mechanist, he's pretty skeptical of explanations that aren't causal. Like, maybe necessity alone isn't enough to explain what's happening in the real world.
It brings up that fundamental question again, what's the connection between an explanation and the actual world? What makes it a real world explanation?
Yeah, for sure. And one way people have tried to bridge that gap is with this counterfactual approach. The idea is that an explanation should tell you how things would be different if something else hadn't happened.
Okay, but how does that work with math, which is all abstract and stuff?
Well, Reutlinger says that a mathematical fact explains something by, governing these counterfactual scenarios. So with the Königsberg bridges, the math of the graph tells you that if you, say, removed one of the bridges, you could walk over all of them once. But there's a risk that this could be too broad. It might count anything that's a necessary condition as an explanation, even if it's not the real explanation.
So just because something's necessary doesn't mean it's the key explanatory factor.
Right. And then you've got other folks like Povich and Barron who are trying to treat math more like a cause. They use these counter-mathematicals, which is basically like, what would happen if basic math was different? Like with the cicadas, imagine if 13 wasn't a prime number. Would those 13-year life cycles still be so advantageous? Probably not, which suggests that the primality of 13 is part of the explanation.
Whoa, that's some serious hypothetical thinking.
Right. And that's one of the issues with this approach. It can get pretty mind-bendy trying to reason about impossible worlds where math works differently. Even Barron himself has been refining his views, questioning whether counter-mathematicals alone are enough to capture what makes a mathematical explanation truly mathematical. He's saying we need to be careful not to confuse cases where math is actually explaining something with cases where it's just representing some other non-mathematical explanation. That stamp example we talked about earlier, that
Yeah.
keeps coming up as a tricky case.
So changing the math in your description changes the outcome, but that doesn't automatically mean the math itself is the deep explanation.
Exactly. And Barron's now leaning more towards this Kitcher-style unificationist view, where an explanation is all about fitting things into a bigger system of knowledge and principles. Lyon also have this program explanation idea that tries to connect mathematical and causal explanations, but even that gets criticized for maybe just sneaking in representations of causal properties within the program.
So we're still struggling to pin down what makes a mathematical explanation truly mathematical in its explanatory power.
Yeah, it's a tricky one. And then, you get some really radical ideas like on phonic structural realism, which says that reality itself is fundamentally mathematical, like the world is made of these abstract structures that math describes. If that's true, then the explanatory power of math wouldn't be so surprising, right? But yeah, that's a whole other can of worms. So at the end of the day, we've got this debate between folks who think all real explanations have to be causal. That's the monism view. And it might have trouble fitting in mathematical explanations, and folks who are okay with different kinds of explanation, the pluralist view. There are even discussions about topological explanations, especially in network science, and whether they're their own thing or just another type of causal explanation. And there's this intriguing idea that maybe expressive elements are essential to all scientific explanations, which could be another way to understand how math fits in.
Wow, so much to think about. It's a really active area of philosophy, trying to figure out exactly how math does this amazing job of illuminating the world around us.
For sure. Now let's shift gears a bit and talk about mathematical models and idealization in scientific explanation. Scientists use mathematical models all the time to understand complex stuff, and those models are often simplified versions of reality. They're not completely accurate, right?
Yeah, like a map, it shows you the important stuff, but it's not the actual terrain.
Exactly. So the question is, if these models can explain things even though they're not perfectly true, does that mean truth isn't actually necessary for explanation?
So can something be explanatory without being totally accurate?
Right. Some people say yes, that the explanatory power of a model doesn't depend on it being completely true. But then others argue that models explain by capturing some crucial truths about the target system, even if they leave out some details. So the challenge then becomes understanding how mathematical models do this representing thing. It's not just that the model looks exactly like the real world.
Yeah. Right, it's more than just a mirror image.
Exactly. Some philosophers think that it involves us, the users of the model, making these connections between the model and the system we're studying. These connections can be complicated, and they often rely on specific conventions and rules of inference. Like, mechanists see models as representing underlying mechanisms, while difference makers see them as showing how changes in one thing lead to changes in another.
So the model's power lies in its ability to highlight key relationships, even if it simplifies things.
Exactly. But then you've got Batterman coming in with a really interesting challenge. He argues that some explanatory models, especially in areas like thermodynamics, which deal with limits and stuff, they don't explain by representing specific features of a system. Instead, it's the mathematical operations and relationships between different models that are doing the explaining. He points to phase transitions as an example, like how systems that seem totally different can behave the same way near a phase transition.
So it's not about finding one perfect model, but about the mathematical connections between different ways of modeling the same phenomenon.
Right, and Batterman says that the mathematical idealization itself is crucial to the explanation in these cases. It's not just a convenient simplification, it's playing a fundamental role. This idea that the idealization is doing more than just simplifying things, that it's actually part of the explanation. It's a big debate in the philosophy of physics.
It suggests that the abstract mathematical framework isn't just describing things, it's actively shaping our understanding in a way that goes beyond just reflecting reality.
Exactly. And of course, there are other viewpoints too. Some argue that you can understand these explanations without these essential idealizations, or that the idealizations are needed to generate the explanation, but aren't actually part of the explanation itself. There are also perspectives that focus on multiple models and using bridge mathematics to connect different levels of description. And then there are cases where you can't just stitch models together mathematically, you need empirical data to guide you.
So it's a complicated picture, but it shows how mathematical models, even with their simplifications, are really powerful tools for scientific understanding.
For sure. Now let's switch gears again and talk about something really fascinating. The idea that the explanatory power of math in science
Hmm.
actually tells us something about the nature of math itself. Specifically, there's this argument that supports mathematical Platonism.
Platonism, that's the idea that mathematical objects like numbers and sets exist independently of our minds, right?
Yeah, like in their own realm or something.
Yeah.
So this argument, it's called the explanatory indispensability argument. The basic idea is that if math is indispensable to our best scientific explanations, then that gives us good reason to believe that those mathematical objects actually exist.
So if we need math to explain the world, then maybe that means the math itself is real in some way.
Exactly. Collivan and Baker are the big names here. Collivan started with a general indispensability argument. We should only believe in the things that are absolutely necessary for our best scientific theories. And math is definitely necessary, so we should believe in mathematical objects.
Seems logical. But wasn't there a challenge to this? Like saying we could use math without actually believing in it?
Yeah, that's Melia's weaseling objection.
Uh-huh.
He said we might just be using math as a tool without needing to believe in all those abstract objects. But Collivan and others argued back, saying it's much harder to weasel your way out when math isn't just being used to formulate theories, but to actually explain things. This led to what's called the explanatory indispensability argument, which Baker really championed.
So the focus shifted from math's usefulness to its explanatory power.
Right. Baker's argument is that we should rationally believe in whatever's indispensable to our best explanatory scientific theories, and math fits the bill. It's kind of like how we reason in science, inference to the best explanation. We believe in electrons even though we can't see them because they're part of our best explanations for how the world works. So the idea is if our best explanation for something relies on, say, prime numbers, maybe we should believe in prime numbers too.
That's an interesting parallel. But surely there are objections to this line of reasoning.
Oh, yeah, tons. One big worry is that it might be circular, begging the question. Steiner and Bangu pointed this out. They say we can't really compare mathematical and non-mathematical explanations if the thing we're trying to explain is already described using math. Like we're using math to explain something that's already framed in mathematical terms.
So how can we tell if the math is doing the real explaining or if it's just built into the way we're describing the problem?
Exactly. Another objection from Satsi is that even if math is all over our explanations, it might just be representing non-mathematical stuff. The argument needs to show that there are distinctively mathematical explanations, where mathematical objects are really doing the explaining, not just acting as a fancy language.
So the question is math itself providing the explanation? Or is it just a clever way of describing some deeper non-mathematical reality?
Right. And then there's mathematical fictionalism with folks like Yablo and Lang. They're fine with those seemingly mathematical explanations in science, but they say we don't actually have to believe in those mathematical objects to make sense of them. Lang, for instance, suggests that they're based on modal truths, like what logically follows from certain mathematical assumptions when you apply them to physical systems.
So we can appreciate math's explanatory power without committing to a whole world of abstract entities.
Exactly. Collivan and Baker, they fight back by saying, hey, it's just like how we accept unobservable entities in science. Show us a plausible, non-mathematical explanation for these things, and then we'll talk. They basically say the burden of proof is on the folks who want to deny those mathematical objects, and that those denials often come from a philosophical bias against Platonism. And then you've got Field, who has a different critique. He says that even if math does explain things, those explanations are always extrinsic and not as good as potential intrinsic non-mathematical explanations.
Lots of back and forth, and it seems like we often hit a wall.
Yeah, for sure. That's why some philosophers think it might be more fruitful to focus on explanation within math itself. Like, can math explain its own stuff? Maybe that'll tell us more about the nature of math.
Okay, so shifting the focus from math explaining the world to math explaining itself. But does explanation even happen within that abstract world of numbers and equations?
Yeah, totally. Mathematicians aren't just obsessed with proving theorems. They also want to understand why those theorems are true. That's where this idea of internal or intra-mathematical explanation comes in.
So one proof of a theorem might be more illuminating, more explanatory than another, even if they're both logically valid.
Exactly. Mathematicians often prefer proofs that reveal the underlying reasons why a theorem is true. They want more than just a chain of logical deductions. They want to see the deeper structure. Thinkers like Bulligand and Brumfield have emphasized this, with Brumfield even saying he prefers certain types of proofs in real algebraic geometry because they're more explanatory.
So it's about gaining genuine insight, not just reaching the right answer.
Right. And there's actually debate about whether proofs by induction are truly explanatory. Lange says they're often not because of symmetry issues, while others, like Baker, disagree. There's also discussion about whether proofs using diagrams or analogies can be explanatory. The key concept here is conceptual grounding, showing the fundamental concepts and relationships that make a theorem true. That's different from, like, metaphysical grounding in some external reality.
Wait, didn't Aristotle talk about this difference between types of proofs way back when?
Yep, he did. He distinguished between demonstrations of the fact and demonstrations of the reasoned fact. Only the second one was truly explanatory for him. And even back then, you had folks like Proclus questioning whether all mathematical proofs really provide that deeper understanding. And that Renaissance debate, the Quaestio Dissertute Mathematicarum, they were also talking about the causality of mathematical demonstrations.
So this idea of what makes a mathematical argument truly illuminating, it's been around for a long time.
Totally. And thinkers like Bolzano, with his ideas of ground and consequence, and Cournot, with his distinction between logical order and rational order, they were really into this. There's also a tradition that connects mathematical explanation to those hypothetico-deductive views of math, where you draw parallels between scientific hypotheses and key concepts in a mathematical proof.
So how do philosophers today tackle this question of explanatory proofs in math?
Well, there are two main approaches, bottom-up and top-down. Bottom-up starts with looking at specific proofs that mathematicians find explanatory and trying to find common features. Hafner and Mancosu and Lange, they've done work like this. Lange, for example, argues that there are different kinds of explanatory proofs based on things like symmetry and simplicity. He uses D'Alembert's theorem as an example.
So using concrete examples to build a general theory of what makes a proof explanatory.
Exactly. The top-down approach starts with a general theory of explanation, often from philosophy of science, and tries to apply it to mathematical proofs. Kitcher's unificationist theory is a good example. It emphasizes how explanations systematize knowledge and simplify things. And externalist models, like Steiner's account, where explanations come from an entity's characterizing properties and those counterfactual accounts, they also fall under this top-down approach.
Counterfactuals, again, even in the abstract world of math, they show up.
Yeah, they're everywhere. In math, counterfactuals are about saying things like, if this mathematical fact wasn't true, then this other thing wouldn't be true either. Philosophers like Reutlinger, Barron, and others have explored this using possible worlds. And then Geisbers has this quasi-interventionist account based on structural equation modeling. But using counterfactuals in math is tricky, you know? Some philosophers question whether it even makes sense to talk about changing fundamental mathematical truths.
Like, what would a world where 2 plus 2 doesn't equal 4 even look like?
Right, it gets weird. And there are other externalist proposals, too. Pincock suggests that explanatory proofs often involve more abstract mathematical entities, and Wilhelm and Podulacy focus on the role of formalization and proof complexity. Then there's the internalist side. Besides Kitcher's unificationism, you've got more recent functional accounts, like the work by Inglis and Mejia Ramos. They use Wilkenfeld's functional model, which says explanations generate understanding, and they add in ideas about how our minds grasp a proof. They say explanatory proofs direct our attention, organize information well, and don't overload our working memory.
So much going on in the philosophy of mathematical explanation. It's a really vibrant field.
Absolutely. And it connects to all sorts of other debates in philosophy, like how we evaluate mathematical explanations is often tied up with ideas about mathematical beauty, elegant methods, deep understanding, and even the style of mathematical work. Exploring those connections can teach us a lot about what we value in math.
And there are parallels with debates in philosophy of mind and moral theory too, right?
Totally. Like, in philosophy of mind, there's the problem of how mental properties can explain physical actions, even though it seems like we already have complete physical explanations. It's kind of like the challenge of understanding how abstract math can explain concrete stuff. And moral theory, there are arguments about whether moral properties can really explain anything, which are similar to some of the criticisms of the indispensability argument for mathematical Platonism. Interestingly, Enoch argues that moral properties are indispensable in practical deliberation, which could be a useful analogy for thinking about math's indispensability.
It's all connected, this big web of philosophical questions.
It really is.
Well, this has been an awesome deep dive into the philosophy of mathematical explanation. We've seen that the question of whether and how math explains, both in the world around us and within math itself, is a really rich and complex one. It seems like even in the supposedly precise world of math, the why behind a truth can be just as important, if not more so, than the that itself.
Absolutely. And for our listeners out there, here's a final thought to chew on. Could the different ways we find mathematical truths explanatory actually tell us something deep about the nature of mathematical understanding, like how it works and how it relates to other kinds of understanding we use in different areas of life? Think about it. Do your criteria for a good mathematical explanation match up with your criteria for a good philosophical explanation? Or are they totally different?